Like Phil said, this is my title. Real quick, this is me. I'm currently a principal incident response engineer with Walmart. I'm on the cybersecurity incident response team. I've been there for about 2 years, a little over 2 years. Previous to that, most of my adult life was in law enforcement, both local and federal. I did a year as a NIFA, a network and forensic analyst with the United States Secret Service, where I was at the National Computer Forensic Institute and oversaw the NITRO program, the Network and Responder program. But previous to that, which is really where this talk comes from, was my time at the Portland Police Bureau in Portland, Oregon, where I spent roughly 18 years, and about 10 of those was in digital forensics. However, there's 2 things on this slide that I get to point out, and I'm going to turn for this. Opinions are mine and mine only, and not that of my employer. And then lastly, all the data that you're going to see in here is fakely generated PII. So not a very big guy, which means I'm not built for prison. So everything in there is 100% fake. All right, this is the outline. What is Tails and how is it used? I think Phil did a really good job of just kind of giving a great overview of that. I'm going to discuss some of the issues that examiners face when they come across a system that's booted into Tails. I'm going to show you guys some ways to collect memory as well as the file system. And then we're going to dive into the analysis of both memory and the file system. And I'm notorious for going long, so I doubt there will be Q&A, but I'll do my best. All right. So what issues do examiners and first responders face when they come across Tails? Typically, it's identifying it. So early on, when I say early on, this goes back to about 2015, 2016, when our investigators and detectives would bring devices and check them into the lab. More often than not, there'd be a USB device that was attached to them. And sometimes it turned out that it was a Tails operating system, and there wasn't much that we could do. We were kind of dead in the water with that. They had no idea that Tails was up and running at that time. We were very fortunate that around 2016, 2017, really aggressive investigator that was part of a task force was like, hey, we need to start having our forensic examiners come out to the search warrants with us and help us identify what's going on in these search warrants so we can collect evidence, like make sure we're not missing things and make sure we're collecting it in a way that we can get access to stuff. Because I was letting them know, hey, we're probably not going to be able to get you what you need because we're kind of dead in the water because of the Lux encryption, which is the next thing. So by default, like Phil alluded, Tails is a great operating system. It is 100% designed for anonymity and security and privacy. It comes preloaded with a lot of tools that support just that. And the big one is it's Lux encrypted, so it uses the Linux unified key setup by default, so being full disk encryption. And the other issue that we face as examiners and doing on scene is access. So without an administrative password, or you're kind of dead in the water for being able to really do any collection, because you need root privilege to run your tooling to get access to do the collection. However, I say this, someone was talking about this earlier, and it might have been Tony. He was talking about, having I think he was, because he talked about the read interview technique, but having good investigators that can do really good interviews on scene, more often than not, we were getting them to hand over their administrative password. So I would say 90% of the time, they would give over that password. The other times that they weren't giving it over, we would either find it written down somewhere, or one of the great things about at least the criminal groups that I was working with, they love to use their mobile devices as their like record keeping and note keeping. So they're notorious for putting passwords in their notes or taking screenshots. So we would dump the phones first and have someone work on the phone and then get the passwords to sometimes get the administrator password. I don't want to confuse, so I'll get to here in a second. Persistence. So by default, there's no persistence in Tails. One of the things that makes Tails, I want to say unique, but interesting, is that it uses the host OS, right? It uses the hardware of the host OS, and it runs in memory. So everything runs in memory. By default, it doesn't have any sort of persistence mechanism, so you can't save anything once it's shut down. Nothing survives a reboot. However, when the user goes to set it up, they do have the option to set up a persistent drive. Again, more often than not, the folks that we were dealing with, and I'll just, the criminal demographic that we were actually really came across us the most was our dark web market vendors that were dealing in the fentanyl trade. And the reason being, we saw this huge spike in like 2018 because we came across a document where they were accessing this site on the dark web on how to set up their criminal marketplace. And one of the recommendations was setting up a Tails OS to do all their work in. And they would set up a persistence drive, and that's where they would keep all their record keeping. What makes the persistent storage drive inside of Tails unique is it's got a separate passphrase that's different than their administrator password. So why do I tell you that? If you're doing your interview and you see that there's persistent storage and you're able to get their administrator password because you need that to run your tools to do your collection, if you do your collection and you don't have the passphrase to that persistent container, and you don't have memory, you're more than likely going to be dead in the water unless they hand it over. I'm going to show you a couple ways in the analysis that you might be able to recover that passphrase. But again, that's why I'm going to kind of emphasize, if you can collect physical memory, I'm going to show you a way that you can get that passphrase from memory and then decrypt that container, which is where all the goodies live. The other thing is like I said, it runs in memory, which is incredibly volatile because it has that inherent trust that once the system shuts down, everything that's in there is gone. All right, what does the collection process look like? So luckily for me, when I came into law enforcement through digital forensics, I didn't come in through a traditional path that most of our peers in this group do, which is typically internet crimes against children or property crimes. I came in through an electronic crimes task force, and we were doing a lot of like malware POS investigations, point of sales investigations. So I came in doing kind of like IR type work in law enforcement. And so I just took that same kind of workflow that you probably all that are in incident response now or have been in incident response use and applied it to this like live analysis. So we collect physical memory. We're going to do targeted collection on disk, right? So we're going to go after those goodies within the file system that we want. And then it's actually pretty quick to get a full disk image just using just the good old DB command because Tails typically isn't very big. So it doesn't, there's not a ton of overhead there. All right. So again, with in order to collect RAM, you're going to, at the very least, need their admin password. Again, it just comes back to you might have to find it written down or get it off of a mobile device or have a really good investigator that does an amazing interview with them. There's various methods for collecting physical memory from Linux. The two that I tested, and again, like I just want to reiterate, this is all test data. I used a tool called Surge from a company called Velexity. And then I also tested Microsoft's AVML. Both worked really well. Both were able to acquire physical memory, and it gives you immediate access to a ton of data really quick if you know how to parse it, right? So that's kind of a caveat there because it can be a little intimidating at first. For triage collection, it's kind of whatever your workflow is. For us, we were going after user folders, log files. The bash history is huge. You can kind of fill in whatever you want. I also tested, there's a script out there called the Linux Baseline and Forensics Triage Tool. It's in beta form. I went and checked it the day before this talk. It's still in beta. And it'll allow you to leverage AVML as well. So you can run this script, it'll collect memory, and it'll go through and collect a bunch of locations or targeted files from the file system and exports those out. However, as I put there in that other point, the script needed a little modifying. I had to modify it because I was having trouble seeing my mount point when I was trying to write out to my responder drive. And I was lucky enough to mention this when I was down at NCFI, and I had a student at the time, I guess he was really bored with my class. He literally like modified the script for me, and so that I could do the input. He actually is a really brilliant programmer, so it worked out really well. One of the nice things about Surge, if you've never used it before, is it's capable of exporting files as well. So it's not just a tool that can collect memory. And you're going to see some examples of that here in a minute when I talk about some of the analysis. But you can script it, you can customize it to get pretty much whatever you need. For a full disk, I basically just used good old DD. It's a free option. That's another thing I should talk about too, is every tool that I use in here except for Surge is free and open source. The Surge tool that I use was my license, not that of my employer. So just want to make sure I get that out there as well. But one of the great things too is, like I said, with Surge, is you can use it to also collect a full disk. So if you look at the bold command line invocation, that's what it would look like, right? So you run the Surge collect binary. You have to give it your user password that you have for your license. The -- files is pointing it at a text file that's sitting in the same directory as the tool. And that is that collection, that triage collection script. And then the -- device, and then point it at the device that you want it to collect, and then the output directory. And that's it. You know, one command line, you've got everything you want, and you're off to the races. The .raw file that you're going to get exported, whether it's from Surge or using DD, is going to be encrypted by default, right? So we're going to still have to deal with decrypting an encrypted drive or partition in this case. The other thing, just to make sure you have plenty of room on your responder drive so that you don't run out of space. There we go. This is just an example of running through the classic DD command, listing the block devices, identifying which one is the tails. Also, when I did this research, you'll see here that SDB partition is a TrueCrypt volume. So I was able to identify a TrueCrypt volume and export that volume out as well, right? So that's pretty important. We would come across that where they would have other devices attached to the physical device if they were booting tails through, and then they were transferring data from external media into their persistent drive. And so this was a way to recreate what we were seeing there. And then the bottom is just running the classic DD command and outputting that to a raw file. And then this is just a rinse and repeat. So this is exactly what I did for the TrueCrypt volume that we saw that was attached. Again, nice thing about this is it's baked into the Tails operating system, so you don't need any extra tooling. You just need their administrative password so you can run this. All right, the fun stuff, the analysis process. So for this talk, it's going to be pretty heavily focused on memory because, again, Tails runs in memory. And that's where I kind of had this aha moment. I've kind of always been sort of a memory nerd and really enjoyed memory forensics. And so this I thought was a really great opportunity to dive deeper into that. Most folks have some experience with Windows memory forensics. I haven't run into a lot of people that I know that do a lot of Linux memory forensics. So this was kind of fun for me. So what I ended up using was, I'm going to show you an example of how to use Yara and a hex editor to pull some really juicy stuff out. Good old strings and grep. So the top two are going to be more of like a cleaver approach to forensics. And then the last one, I'm going to show you some really unique examples, or what I think are some good examples on how to leverage volatility, the most current version, which is volatility 3. And then we'll dive into some file system analysis where we're going to decrypt the LUX partition because we're going to recover the key in memory. And then I'm really excited about this, and I'll get there in a minute. I don't want to spoil it, but I'm really excited about this. We're going to then mount that decrypted partition, and then we'll be able to analyze that mounted partition in the command line. All right, so memory analysis. Like I said, volatility 3 is more of like your scalpel approach. What was really, again, what got me really kind of excited about being able to do this talk was as I was preparing to submit it, I'd started this research back in 2023. And even though volatility 3 was around in 2023, it did not have a mature Linux plugin architecture. So there was not a lot of plugins available to do Linux memory analysis. It wasn't until probably about 3 months ago that the Volatility Foundation kind of put an announcement out there and said, hey, we believe we have feature parity between volatility 3 and volatility 2. Therefore, we're releasing it from beta and just saying, hey, here we go. And in fact, they had. So there was a lot of plugins that for years, volatility 3 was missing that volatility 2 had for doing Linux analysis that they now have. So super excited about that. In red, though, you're going to see that there's no Linux symbols tables. Well, let me rephrase that, however I want to phrase that. There's no symbols tables for the Tails version of Linux that are in the default package that you would get off of the GitHub repository for volatility. which means you're going to end up having to either build your own symbols table, or hopefully someone out there in the community has built one already that you. They're not incredibly hard to do, just a little cumbersome. I would say if you end up building some of these symbols tables and you have a GitHub, it would be nice if you pushed them out to the community, because it makes saves a lot of time for all of us. The next thing I did was, what we're going to see is just using Yara. I'm sure a lot of you in here have used Yara, or maybe use it in your current jobs. But a lot of people don't think of using Yara for user investigations. They really just think about using it for, like, cybersecurity, malware, and incident response type investigations, or maybe they're using Yara to do like retro hunts or something like that. And then strings. We're going to do some strings-based searching using grep, or you can use your favorite text editor, however you want to do it. Those are the three tools that we use for memory, but there are other stream-based data carvers out there that are free and open source that will carve this memory image for you and get you some data. But for the sake of this talk, having 35 minutes, I had to limit the toolbox that we use. All right. So this is a very, very simple Yara rule. You're probably not going to be able to read it, but essentially what it is a bunch of strings that have to do with things like passwords, and then things like credit card cloning, or PII, or Veracrypt and Bitcoin wallets and things like that, because that's what this data set is based off of. It's going to be based off of like financial fraud, credit card fraud. That's kind of like our bad guy. So back up, I guess, real quick. So this is that's all it is. Super simple, nothing complex about it. And I guarantee there's probably at least one typo in there. So this is running it, right? So I'm basically saying I'm running Yara. I'm giving it the -s flag because I want it to identify every string that it matches in my Yara rule. And I need the physical offset of where that rule matches in memory, because that's incredibly important. I write that out to a text file. And then from that text file, then I can just throw it in a tool like less, right? Or you can grep through it if you want. But what I like to do with this is I'll throw it in less, and I'll use the /, which then gives me the search capability. And you can see here, I'm just searching for the string MasterCard. And it points to every single hit that Yara rule matched. And here, I'll end up looking at this, but I will. And for example, I just pick one. So this is kind of, like I said, it's not really that scalpel or targeted approach. You kind of have to be a little patient and like ruthlessly go through this, sort of pick a couple and see what it does for you. More often than not, you get pretty lucky. You always get something useful out of it. So here I have the physical offset in memory. And then I'm able to use XXD, which is a hex editor from the command line. I guess I should back up one step too. I did all the analysis in a Linux VM, so there's going to be a lot of Linux commands as I work through this analysis. Using the -s, I'm saying seek to this physical offset, and then show me the 512 bytes after that location, and point it to my memory capture, which is that tails.lime, and I truncated the output because that's definitely not 512 bytes, but you're gonna see what looks like MasterCard numbers. Again, fakely generated, not real. So really quick, easy way to start getting to some data, right? With just having memory. Rinse and repeat, doing the same thing. This time I'm searching for the string Veracrypt, because if you remember when we were looking at the block devices, I saw what looked like what I could reasonably believe to be a Veracrypt drive that was attached. And so doing the exact same thing, I grab one of those physical offsets, jump back into XXD, seek that offset. In this case, kind of learned my lesson. I dropped it down to 128 bytes. And I can see reference to a Veracrypt volume. It's just a way for me to quickly build some intel and start looking for some of those forensic goodies that we can continue to, when we do go to the scalpel approach, that we can start carving and pulling some of this data out. And one last, we had a username. Our user's name is Gymnasium. So I did the exact same thing. I basically just threw it in less, did the search feature, picked one of those physical offsets. The only difference here was, by this point, I'm starting to clean things up a little bit. So I'm dropping it down. I'm, again, running XXD from the command line, saying this offset, show me the trailing 64 bytes. But instead of just giving me everything, like I didn't care about the hex, I just wanted the ASCII output. I piped it out to awk and said, just give me, I knew that it was the 10th line, so I used awk to show me what the ASCII output was. And what I ultimately ended up getting here is Gymnasium's email address, right? So that's great. So now I have a Gmail address. So something I could pass off, and you could start doing legal process on that Gmail address, or you could use that for other things. All right, some strings-based analysis. So really straightforward. Like I'm sure you guys do this all the time. In this case, I just ran the strings so that I would get both ASCII and Unicode output. Basically just, wrote that out to a giant text file and then just started grepping through that text file for keywords that we had. We knew that we had, that he was using, that our bad guy was using Electrum wallet. So in this particular instance, I'm grepping using the case insensitive for Electrum wallet. And what's nice about this is I get what reasonably looks like to be a password. And ultimately that is, spoiler alert, that's the password for Gymnasium's Electrum wallet. I won't do anything because that wallet's no longer active, but that's the password for Gymnasium Electrum wallet. So that's a huge win right there. If you're like on a task force or for law enforcement that's going to do like asset forfeiture, right, and seize those assets, it's a great way to get into the wallet and steal assets. We had seen a reference before to MasterCard. So let's see what the strings output from the memory dump gives us. And here we get all kinds of stuff, but we see a reference to a MasterCard.txt, which more likely than not is a dump file or a bin dump of a bunch of MasterCard credit cards that then they'll use just into like a card reader to clone credit cards. And right below it, you see a string on cloning a MasterCard, right? So that could be a potential search that this person did. And then there's a bunch of stuff that looks like PII that's associated to MasterCards. And then at the bottom, what's interesting about this is we see reference to an attached device, which, spoiler alert, is that TrueCrypt. That TrueCrypt was named the vault. And inside the vault is a text file called MasterCard.txt. So now we're getting reference to the file system on where some of the artifacts or these evidence objects might reside that we can then try to go and hunt for even further. Like this is great, this is really good information, but most like prosecuting attorneys kind of want the smoking gun, right? Like they want the actual document. And I'm going to show you that we're going to be able to go in and recover most of these documents. Same thing, reference to the_money. It was another, like again, might be going, hey Aaron, how did you come up with all those strings for your Yara rule? A lot of times we'll just look at the notes that they have kind of written around on their desk, and we'll see references to, just things that just of interest. And we'll put those into our Yara rule, or we'll use those as our starting points for doing string searches. So we saw a reference to, or I saw a reference to the money. And in this case, I'm just saying, hey, I want to see everything before, 5 before, 5 after by using grep. And here you can see what looks like another password, right, or passphrase. And in this particular instance, it is, this ultimately ends up being a really useful passphrase. All right. So again, that was like a cleaver approach to doing this. It gives us a lot of useful information, and some might be happy with that. Like, hey, that's enough for me to have a smoking gun, or that's enough for me to prosecute, or that's enough for me to close my case. However, most prosecutors, like I said, like to have the actual object itself. So we're going to use volatility for that. One of the caveats, like I said before, is if you don't have the proper symbols for that particular version of Linux, then you're going to have to go and either build it yourself or get it from the community. The way you can check that is, if you remember from Volatility 2.6, there was a plugin called Image Info. This is kind of the basic like Volatility's 3 version of Image Info. We're just running the banners plugin, which will identify the build and version of the Linux kernel for you. And you can either search to see if someone else has a symbols table for you out there to grab and pull in, or you can go build it yourself. Luckily for me, I was able to find, so I started research in 2023, did a collection in 2023, then I did one in 2025 because I wanted to see how much it changed. between the two Tails operating systems, and both builds are out there. And there's going to be a link at the end that'll show you where you can go on GitHub, find a bunch of these symbols, pull into your volatility. You do have to create a Linux directory and then dump those into that Linux directory, because that's how the tool will read to pull for those symbols. And that's all I'm doing there, is just showing where you'd put it. So now that we know that we've got the actual symbols table for that particular build, we can start ripping through and doing a bunch of scalpel type analysis. Look at the boot time. This is a great plugin because you can see when it was booted, see if it aligns or correlates to whatever investigation you're doing. However, what's really juicy and helpful is running the Linux bash plugin to see their bash history. Just like those of you that probably do IR work, if you're ever investigating a Linux or a Mac endpoint, the bash history is incredibly important. But here you can see some things I highlighted, like the user's making a directory called the goods. They're moving the goods to the persistent directory, or that persistent drive that I said that was stood up in the beginning. They're making a directory called images. They're changing the permissions so that they can actually run their Treasure wallet, which is like a Bitcoin wallet. So you're starting to see some interesting stuff. There's a wget to like pulling down a credit card image, like a JPEG credit card image. So you can start profiling the user super quick. All right, so how do we get evidence objects? We've got the memory capture. So one of the really cool things that we can use is a new plugin is the page cache files. And so what I'm doing here is I'm running volatility against my memory image. I'm saying render it in the pretty mode, and then I'm running a plugin, and then I'm piping it to grep, and I'm looking for anything that's in that persistence drive. What it gives me is some incredibly useful information, and that's the stuff that's highlighted in red. The first thing I get on the first line, that's that 260.199, that's the inode for this particular visa.txt. And then I get the physical address for that inode in memory. So those two things are incredibly important, because having those, I can potentially go and recover that file object from memory. And if you look, I just did the exact same thing for all these. But you can see, like, you'll see, the goods dot spreadsheet for the goods. You'll see a spreadsheet or a TXT for a bunch of credit card numbers. And again, it renders the stuff that you want. You get the inode number and the physical address in memory where to go get it. All right. So I'm rinsing and repeating, and I'm doing it for MasterCard. The only difference here is I'm starting to see that this MasterCard.txt might live in two separate places within our Tails OS. I see reference to the vault, which was that TrueCrypt volume that was plugged in. So we captured it, but it's also referencing a file object in memory of the Tails OS of a document that lived on an external drive. That's pretty cool. And we might want to go capture that. All right. So instead of just grepping through it, I wrote it to a text file, and then I grepped that text file, right? So now I've got a master text file of every file object that's living in memory that I can potentially go and recover. And so grep through it till your heart's content on those things that are important to you. I'm just showing a couple examples here, like looking for like their documents folder and seeing what might live in their documents folder. But also you can go and look for, specific artifacts that are, relevant to like the Linux operating system. So in the bottom example, like I want to go look at the history log for apt to see if they installed any packages. And you can potentially export out that log and then do log analysis. Kind of cool. All right. But then what we want to do is we want to be able to dump this stuff, right? So there's a plugin called Page Cache inodes pages. And so what we do is we take the physical address of the inode that we saw in the previous plugin, and we basically just dump that inode. And that's what's happening here. So I'm giving an output directory called inodes. I'm running this plugin that's essentially, it's basically like, you remember dump files from Volatility 2.6. That's essentially what this is the dump files plugin. And then -- inode, and you got to give it the physical address of that inode, and then the -- dump command, and it dumps. And you can see here that it dumps it to the inodes directory. I got a dump file, and you cat that dump file, and that is that credit card dump, right? So that's that's actually really useful. Rinse and repeat. So we're doing it for wallet, and here I'm looking for anything that this is what I'm looking for, cryptocurrency wallets, and I'm using the exact same workflow. So I'm finding the inode, pointing the plugin at the inode, dumping it, and then looking to see what's in the output of that. And again, we're seeing what looks like an Electrum wallet password. So that's great. That's a huge win for us. We can, other than just text files, we can also dump spreadsheets, images, and you're gonna see that as well. Here, I was showing you that you can either dump by inode, or if you know the actual path on disk where that file object resided, then you can, like in the second bullet point, instead of using the -- inode, I'm doing the -- find condition and then pointing it to the exact path. So if you know the map path on disk where maybe a log file is that you want, you can like Etsy shadow or Etsy password, or you want to crack passwords, you could go grab and recover those. In this case, I'm just dumping a spreadsheet, and then if I can help it, I never want to leave my terminal when I'm doing my analysis. So I'm launching LibreOffice from the terminal and just basically looking at what the document. And again, this is just a bunch of what is fakely generated PII. And then rinse and repeat, doing it one more time just to show that you can also recover images, right? So folks that are doing investigations where images might be incredibly important, you can recover images as well. This is another example of recovery. All right, I got 3 minutes through the file system, how it goes. So here we're just, I'm just running the MMLS command, the sleuthkit command, to get an idea of where my tails volume sits, because I need a couple numbers in here. And I want to see what I'm dealing with at that offset. I'm dealing with an encrypted, Lux encrypted drive. So that's kind of a bummer. However, all is not lost, because there is a tool that's going to be released probably in October called Keyhound. It's not mine. Elijah Brigham is releasing it. Peer of ours in the law enforcement community, that goes in and will recover the Lux key from memory. And then, which is what I'm doing here because I'm trying to move fast, but running this Keyhound binary against the memory image, and it dumps out and finds 2 Lux keys. And then on the next screen, what I'm doing is I'm basically taking the image that the encrypted image, and mapping it to figure out what my loop device is going to be, so I can map it and mount it and decrypt it, which you're going to see here. I'm actually creating a key file. So on the top line, I'm echoing that long string, and then I'm piping it to XXD, and I'm writing that to a binary file and calling it key_1 file. And then I'm using the crypt setup library inside of Linux and the master key file plugin, and pointing it at that new binary key file that we built and saying Lux open, and I'm pointing it at the mapped encrypted drive, which in this case is loopback 17 partition 2, and then pointing that so that it then will uncrypt. And you'll see here that at that point, now that it's decrypted, we can mount it. And so we can just mount that tails, in this case, I was calling it tails, but we can mount that decrypted tails partition to our analysis system and then start looking through it. The 2 bottom lines, if you had to do it manually, there's some manual stuff where you might get some permission issues. You got to go in and just change some permission issues. So luckily, there's only a couple slides left. Here, this is just showing that we've now decrypted that persistent partition that was encrypted, and we can start using our Linux host system that we're doing our analysis on, and I'm running the tree command against that persistent drive that was decrypted, and you're seeing all the stuff that's sitting in their directory. So in this case, it's just a bunch of like text files that hold credit card numbers. And we can just start looking at what might be inside some of those files, just using the cat command, right? Because we're just directing it, pointing it right at those text files. And this just happens to be a PGP key that's sitting in the notes inside that persistent drive. So we have full access to that, what once was a Lux encrypted drive. Ooh, I did it with 41 seconds. I kind of had to move fast. I knew I was going to have to move fast. But here's all the resources. Again, super excited for Keyhound. I'm excited for when that comes out in October. And the one above that, on the very bottom here, is where you can go to find a lot of symbols that have already been created. So if you're doing Linux Memory analysis, that's where you can go to find it. And I would say questions, but I got 19 seconds. So that's it.